Good afternoon, everyone. As Chief Scientific Officer at Vitrolife, it is my pleasure to welcome you to our ESHRE 2020 Scientific Symposium on how artificial intelligence will empower your decisions. AI is being employed in numerous areas of our lives, and it is certainly poised to dramatically challenge or change healthcare. Today, we have two fantastic presentations on this topic. Dr. Aengus Tran will provide insight into how AI is being brought to the patient's bedside. Aengus is an MD and is the CEO and co-founder of Harrison.AI, which is an exciting and fast-growing company focusing on healthcare products and services that utilize AI. As many of you know, Aengus's first product in the IVF field, called Ivy, used time-lapse videos for automated embryo evaluation and was developed in collaboration with Virtus Health. Vitrolife acquired this technology in April 2019 and has further developed the technology. Jens Rimestad is a member of Vitrolife's deep learning team, and he will talk today on how that technology has been developed and validated to develop an AI-based tool, iDAScore, which is designed for embryo evaluation. There will not be a Q&A session at the end of this presentation. Instead, we will use the chat function to answer as many questions as possible. But before we start the two presentations, we would like to take this opportunity to remember and celebrate Professor Michelle Lane, who we sadly lost in February of this year. I would therefore like to invite Professor David Gardner to reflect on Michelle's contributions to embryology and the IVF field. Over to you, David.
Thank you, Mark. In my entire career, this is without doubt the saddest thing I've ever been asked to do. On the 4th of February this year, the world of IVF lost a true great scientist and wonderful laboratory director. Michelle Lane lost her long battle with illness and sadly passed at the age of just 49. Although many of you will know her name and know her papers, perhaps you don't know her career. So I'd like to take just a few minutes to talk about Michelle's amazing contributions to science and IVF. Michelle started her journey in embryology at the age of 20. She was an undergraduate student and she came to work in my lab at Monash University. Following on from that, Michelle stayed with me as a research assistant as we started our journey on investigating the role of amino acids in regulating embryo development. And it was during this time that it became evident that Michelle was really a very smart individual and had the capacity to do a lot more with her career. So I encouraged her to undertake a PhD, which she gratefully accepted. And over the ensuing years, Michelle showed herself to be just an incredible student. These were really exceptional times in the laboratory and for embryology, as we saw one by one the blocks to in vitro development move away as we were able to culture mouse embryos, then sheep, goat, cattle, and eventually the human. During this time, Michelle had no problems completing her PhD, and she did so with great aplomb and on time. And as soon as she'd finished, she'd already had a job offer, and she moved to Madison, Wisconsin to go and work with Professor Barry Bavister. I remember she left Australia on a very hot summer's day. It was 40 degrees Celsius here in Melbourne. And by the time she got to Madison, Wisconsin, it was minus 20 degrees Celsius. I remember she emailed me the next day to let me know that, you know, it's cold when the snuff in your nose freezes, and she didn't say snuff. She had an incredible period with Bavister and published many, many papers. After which I was fortunate enough to work with her again. I moved to Denver in 1997, and in 98 she came to join us, and we embarked upon a series of translational studies which facilitated the way to single blastocyst transfer. And then in 2003, Michelle finally headed home, and she moved to Adelaide, where she rapidly set up her own independent research and soon became the scientific director of Repromed, and indeed became a full professor in her own right. This was Mitch's first paper, published in 1992 from that very first project that she undertook. And this was the first in a large number of papers, 79 papers we published in the following 3 decades. Her research interests were many. During her PhD, she looked at ammonium and birth defects, how amino acids regulated embryo development, and metabolism as a marker of viability. In Wisconsin, she pioneered containerless vitrification, developing the cryoloop, and she also worked extensively on pH regulation in embryos. When she moved back to Australia, into Adelaide, she worked on how stress compromises embryo development, and her latter studies really focused on paternal diet on embryo development and offspring health. And this culminated in this really exceptional review that she wrote in the journal Science, Parenting Before Conception. When trying to assess somebody's career, you can turn to the metrics, and here you can see her citations. She had 20,000 citations and an H factor of 75. Now that's outstanding for someone who's had a full career and retired. For someone at the age of 49, it's somewhat miraculous and just reflects her incredible work ethic. But more than that, metrics don't really reflect the translation of her work. And there's literally hundreds of thousands of couples out there who have got a family now, thanks to her basic research and translational research. You can judge a career also by the legacy of those you've trained. I was very fortunate to be trained by the great and brilliant Henry Lees, and it was my fortune to train the great and brilliant Michelle Lane, who went on to train Deirdre Zander-Fox, who trained Nicole McPherson. There was a whole group, many students that Michelle went on to train. And I think it's through them that her legacy, her life's work will live on. We will all have our own ways of remembering Michelle. For me, it will always be as that graduate student. Michelle wanted nothing more than to set out and help people and to improve the success rates of human IVF, which she did. So now, what can I say? With regards to IVF, one of the only constants is change. And one of the changes we've experienced in the last 3 years is the rise of artificial intelligence and its use. So I'd like to introduce now Aengus Tran, who will talk about artificial intelligence from bench to bedside.
Good afternoon, everybody, or morning, depending on when you're watching this video. My name is Aengus. I'm a medical doctor, so I'm currently working at the Medical AI Directors at Harrison.AI. We build AI tools for clinicians to help empower them develop better, faster, and cheaper healthcare for the mass. So today it's my pleasure to talk to you about AI from AI to bedside, a journey in taking this innovative technology from ideas to the bedside and serving patients. So it's probably useful to take a step back and think about the evolution of AI in healthcare. So artificial intelligence, AI, is a very old concept. This has been around since the 50s. And AI is loosely defined as any computing system that can perform cognitive tasks, so tasks that resemble human intelligence. And because of this broad concept, even very simple systems such as a rule-based system that look at the heart rate if it's under 50 beats per minute, called a nurse. This can actually be considered an AI system. And in the 50s, this dominates the fields where people trying to write extensive rules to describe very highly complex cognitive tasks. And as you can imagine, this is not a very scalable approach because if we cannot write down on papers how to do certain tasks, it is very difficult to program a software to perform these tasks in this way. Because of that, we didn't make tremendous progress in the field. And in the 80s, a different kind of approach to solve intelligence has emerged called machine learning, which focusing at instead of teaching the algorithm to do exactly what we want it to do. We actually teach the algorithm how to learn, and by feeding it a large amount of data, we can teach the system to perform highly sophisticated tasks without explicitly telling it how to do so. For example, by collecting blood tests, vital sign monitoring, one can build a system that statistically learn to predict whether or not the patient will have sepsis based on past observation. And this field has developed a lot able to build sophisticated statistical model to estimate this unlikely event. But once again, the limitation of these algorithms is the expressiveness. When the problem become highly complex, these statistical models start to break down and is unable to find meaningful patterns. And recently, in the 2010s, a new wave of artificial intelligence approach has arrived called deep learning, which is basically statistical model but on steroid, where we have powerful neural network algorithm that mimic the way the human brain works and is able to leverage tremendous amount of data that arise within the past couple of decades and able to extract and learn powerful representation, such as directly at pixel level data from images. So now we can solve issues like what are the chances that the patient have pneumothorax or pneumonia on a chest X-ray. And this has given rise to a host of potential solution in healthcare. It all starts with a single most important data set in the entire deep learning field. It's called ImageNet. It is a data set of millions of day-to-day objects that's collected on the internet and has been labeled by human for which images contain what objects, such as car, coffee cups, donuts, that kind of objects. And using this data set, a competition was created. It's called the ImageNet competition, where every year researchers trying to build algorithms, trying to predict what object is in these images at the highest accuracy possible and trying to reduce the error in doing so. As you can see, in the 2010 and 11, the error rate was anywhere between 28 to 26, meaning that 1 every 4 images would contain an error in prediction. And because of this was not very useful in any practical application other than research. But magically, something happened in 2012 where there was a big performance jump from 26 to 16. And this is called the AlexNet moment, where researchers for the very first time is able to build an algorithms that able to reduce the error rate in ImageNet without hand coding the features, what is in the image, such as cat have pointy ears or car has 4 tires and that kind of thing. It's learned directly from the data using massive amount of compute. And ever since, the progress has been tremendous in driving down the error rate of this visual recognition system using artificial intelligence. And in 2015, it's the very first time we passed the human performance in doing the same task. So we clearly has transitioned from the age of discovery, where it's primarily about computer vision research, into the age of implementation, where we can take these computer vision system that is superhuman and apply that into meaningful problems in healthcare and solving it meaningfully. If I'm able to summarize what AI is, it is this. AI lower the cost of prediction. We've seen this before in other technologies, such as the computer chips. The reduction in cost of silicon chips able to build these computing system at low cost. And because of this, everything we do today is around computer chips. Even turning on a microwave involves a microtransistor that's more powerful than a machine that sent man to the moon. And the fact that we can do this recording today over the internet is all due to the reduction in cost of arithmetic through this computing system. What would happen when the prediction itself has a reduction in price? We know that when something becomes cheaper, we do more of it and we can solve more problem with it. So in healthcare, we are surrounded by predictions. You may not know it, but when we walk into a clinic, the nurses make prediction about how sick we are and whether or not we need to stay or go home. When we take a chest X-ray, a radiologist need to make a visual predictions on whether or not there are pathologies. When a clinician reads a medical report, they need to predict whether or not those patterns of symptoms and signs and medication you take result in a risk of further complications or disease. And every day, our doctors looking at blood tests, vital sign, and past history in order to make a determination about the likelihood of deterioration, such as sepsis and myocardial infarction in this example. So medicine is surrounded by predictions, and the reduction in cost for prediction using artificial intelligence is an incredibly exciting thing. But how do we harness this technology and turn it from research into the bedside? At Harrison, we had the fortunate partnership with Virtus Health, one of the largest IVF providers in the world, in developed technology we call IV. That's allowed the embryologist to select the best embryo possible for transfer. And we would like to share with you today the 8 steps that we went through in converting these very novel ideas into a practical application benefiting patients around the world. The very first step is always to ask the right questions. And in IVF, one of the most important questions is which embryo will have the best chance of create a pregnancy. Because if we can do this, we can reduce the time to pregnancy by prioritizing the embryo with highest viability first. Here's the videos, a time-lapse videos of human embryo growing inside Vitrolife time-lapse incubator for 5 days. And the problem we're trying to solve is to look at this video and estimate the chance that each of these 12 embryos will result in a pregnancy. The second step is always about collecting large amount of data. We all have heard that data is the new oil. But I would contest, label data is the new oil. Because without the label, without the outcome, there's no way to teach these algorithms about the nuances of embryo development. That's why this 10,000 embryo dataset has been labeled by the pregnancy outcome as determined by fetal-heart pregnancy. And that is the signal that we use to teach this algorithm to learn for itself what video is correlated with the best pregnancy potential. The fourth step is to handcraft the best AI algorithms using the state-of-the-art architecture. Unlike what may have been taught in traditional media, this algorithm is highly tuned and is highly customized to serve the purpose. For example, we have developed algorithms that look at the entire time-lapse video sequence, which examine every hours of embryo development throughout the 5-day process. This is much superior comparing to analyzing the image at the very last day of the 5-day development cycle, because we get much richer data about how the embryo developed instead of just how it looked at the very end. And most importantly, making this algorithm explainable. Here's a visualization of IV algorithms, focusing on different sections of the video. The red being the area that contribute the most to viability of the embryo, and the blue is the area that contribute to the non-viability of the embryo. And as you can see, without ever teaching the algorithm about embryo development, the algorithm figure out for itself different sections, highlighting the molar compaction here, for example, as a key developmental event. We also need a lot of compute. So we got this supercomputer that we built, and we trained it on the 10,000 embryo dataset, and is able to reach expert level performance in predicting the pregnancy outcome as determined by fetal-heart pregnancy. We have papers published in Human Reproduction that detail this work, but it's important to highlight that these solutions are inherently medical device and require rigorous validation and highest level of evidence before they can go into clinical practice. The final step of the journey is to put it in the hand of clinicians and integrate seamlessly to their day-to-day workflow so that they can take advantage of this technology and support their work. IV has been deployed over the last 12 months in many clinics across Australia, and we are very proud of this. Soon, this algorithm will be available through Vitrolife in every device. And recently, Harrison has partnered with Vitrolife with the development of iDAScore, the next generation algorithms that is the follow-up work to Ivy, which much more power, expressiveness, and train on much richer, diverse data set of data. I would be happy to pass it on to Jen later to talk about this. And if we do everything right, this is what we are rewarded with. This is the articles in Courier Mail that features a baby that was born with the assistance of the IV algorithm in selecting the best possible embryo for this mom. Here's the 8th step again. We need to ask the right question, gather a big amount of data, label this data effectively and quickly, handcraft the best AI algorithms and architectures using state-of-the-art methods and best practice engineering, train the AI algorithms on a supercomputer and highly tune them for best discriminative power, rigorous scientific validations and regulatory approval, and as well as seamless deployment into existing workflow, and have a good partners to distribute that so that can be in the hands of clinicians all over the world. Before I pass it on to Jen to present how iDAScore was developed, I just want to leave you with a framework on how to pass the complexities of bringing an AI solution from ideas to bedside. It is an idea taken out of a book called Prediction Machine, which is adapted toward the use in healthcare. There are 6 questions that each of us have to ask before we can apply an AI solution into a problem in healthcare. The first row deal with the ideas itself and the validity, while the second row deal with the technical challenges with building these algorithms. The first box called prediction. What is it that we are trying to predict? In the case of Ivy, we're trying to predict whether an embryo one transfer will lead to a successful pregnancy with fetal heartbeat at 6 weeks. The judgment here is that IVF is a highly emotional and financially expensive endeavor for couples. So we don't want them to have repeated cycle. We want them to have the best chance of pregnancy as early as possible. The actions, once we predict the best possible embryo, is for the embryologist and the gynecologist to transfer the best embryo for the patient, resulting in a successful pregnancy. And the outcome that we're looking for is the accuracy of these algorithms in predicting that outcome. To develop these algorithms, we need an input data set of time-lapse videos in the time-lapse incubator for 5 days. And the training data is the pregnancy outcome that come along with those training video. It's also important to note that these algorithms are not static, and feedback data is required once the algorithm is deployed, so the algorithm can continue to learn and improve based on real-world statistics. And finally, the value here is that we reduce the emotional and financial burden of IVF patients while improving health equity and making the traditional subjective process much more objective, which is the goal that we're looking to achieve. Next, I would like to pass it on to Jen to present the iDAScore and developments of the next generation algorithms. Thank you so much for your time.
Thank you, Aengus. My name is Jens Rimestad, and I'm a deep learning specialist at Vitrolife, where I work in the technology division as part of the AI team. In this presentation, I would like to present the development and evaluation of our latest embryo evaluation platform called iDAScore. But before I start, I need to disclose that I am a Vitrolife employee and also shareholder. First off, let's take a look at how embryo annotation and selection is done currently on Vitrolife time-lapse systems. Often, an embryologist look at the sequence and annotate morphological and morphokinetic events. The annotations are then used by either an expert or a model, like, for instance, Vitrolife's KidScore, to predict a ranking of all embryos, so that an embryo can be selected for transfer and embryos can be selected for freezing. Vitrolife's guided annotation version 2 replicates this indirect approach to scoring embryos. The advantage of indirect methods are that they are somewhat transparent. The embryologist can for themselves verify the predictions performed by the AI and potentially modify them for better scoring. The disadvantage being that the annotations used to make the AI are based on annotations known to be prone to inter- and inter-observer variability. To avoid restricting the AI to the precision of the expert knowledge, we can take the direct route, shown here, which, given the raw time-lapse image sequence, directly predict an objective event. Here, the objective event can be, for instance, pregnancy, gestational sex, fetal heartbeat, or ultimately live birth. Because of the added predictive power and consistency, we believe the future of AI methods for embryo selection will be based on the direct prediction of the chance of pregnancy based on these raw time-lapse videos. Our latest assistant is called iDAScore, which stands for Intelligent Data Analysis for Embryo Evaluation. iDAScore is based on a technology by Harrison.AI, acquired by Vitrolife in the beginning of 2019, called Ivy. Information on the original method can be found in the Human Reproduction publication by Tran et al. Listed here below. Our team of AI specialists and software developers have, together with Harrison and Vertus, worked hard to mature the algorithm and integrate it with our time-lapse systems. So how do iDAScore work? Inside the iDAScore algorithm, a 3D convolutional deep neural network analyzed the entire time-lapse video of the developing embryo and compute a score for each embryo. A deep neural network is a mathematical model that can learn to extract and condense knowledge from raw data and turn it into predictions. Since we use 3D structures inside our neural network, we not only look at 2D spatial content, like how does the embryo look at a certain time, nor only at 1D temporal information, like when the embryo divided from 2 to 3 cells or form a blastocyst, but morphodynamic information of how every part of the embryo changes over time. This lets the neural network learn from all the information available in time-lapse data. The score that iDAScore provides describes the embryo's potential to implant and result in a fetal heartbeat. The original Ivy algorithm was developed on full time-lapse sequences from 8 different clinics using more than 8,000 embryos, of which nearly 700 had resulted in a positive fetal heart. With iDAScore, we have managed to raise the numbers to 18 clinics, with a total of more than 115,000 embryos, of which more than 4,000 were positive pregnancies. This is important because with AI methods, and deep learning in particular, the algorithms continue to get better with more data. The discards here are embryos actively deselected for either transfer or freeze by embryologists because of either PDT aneuploidy, arrested development, failed fertilization, 3PN, or some other clinical deselection. It makes very much sense to include discarded embryos in training, since we are working towards fully automatic embryo evaluation, where every embryo needs to be evaluated correctly. To evaluate iDAScore, we have set aside more than 17,000 embryos out of the total 115,000 as a holdout test set. That is a data set with embryos never seen by the AI during training. On this test set, we get an overall AUC of 0.95. AUC is the area under the receiver operating characteristic curve, which is a ranking metric that for each score threshold calculates a sensitivity and specificity point on a curve. The AUC is the area under this curve. A perfect model will have an AUC close to 1, and a model returning random predictions will have an AUC of 0.5. An AUC of 0.95 tells us that iDAScore has truly learned how to distinguish good quality embryos from low quality embryos, based solely on time-lapse information and information of whether they resulted in a fetal heartbeat or not. So how do we actually train these deep neural networks? Training of deep neural networks is called deep learning, and it's a cyclic process where a set of data with known labels are shown to the model. The error the model made for each sample is calculated using a loss function and used to adjust the model for the next iteration. This process continues for thousands or millions of iterations until the model cannot gain additional knowledge from the data. A lot of parameters need to be tuned manually for optimal performance of a neural network. Some of the more important are how the data looks. For instance, how many focal planes are used, how often are frames sampled and shown to the model, and then something called data augmentation is used to change the data while training. I'll come back to that in a second. Then there's data sampling. How often is positive and negative labels shown to the model during training, and how often are the different clinics sampled? And then there's the overall network structure, like the size of it, how complex is the model, and then the architecture, that is the building blocks used to build this neural network. And then finally, there's this loss function that I mentioned just a second ago, which is used to compute the error. That is variable as well. But before we start training, we need to clean our input data. Since deep learning finds the best and easiest way of scoring our embryos, we need to remove subtle clues of embryo selection and misleading information before we start training. In some cycles, one embryo is removed for instance, a fresh transfer, and the remaining embryos are cultured further. An example of such a sequence is shown on top here. The images of the empty wells from the transferred embryos are telling the computer which embryos was actually selected by the embryologist. Thereby, the computer learns that an empty well is a positive trait and expected for good-looking embryos. Therefore, we need to blank it out. It is not only the time-lapse sequence that needs to be checked before use. Labels need to be standardized as well as sanity checked to avoid incorrect labels, like, for instance, a discarded fetal heartbeat, positive fetal heartbeat. We have used a lot of time organizing and filtering time-lapse sequences to avoid training on invalid and incorrect data. Let's talk a bit about data augmentation. When feeding the cleaned input data to the neural network during training, we would like it to learn general concepts of embryo evaluation and not just recognize one sequence from another. Recognition can happen since we need to show the same data to the neural network many times for it to learn everything there is to learn. Therefore, we make small changes to the time-lapse sequence before each prediction step, and this is called data augmentation. One of the great things with our time-lapse systems is the fine-grained fidelity of data. We have up to 11 focal planes and 10 to 15 minutes between frames. This is great for manual inspection, but not strictly needed for the current level of neural network complexity. Therefore, we can obtain different but similar data from each time-lapse sequence just by changing the focal plane, as shown on the left here, offsetting the start time, as shown in the center, where the red line indicates the frame used as start image, or by picking neighbor frames to the base sampling distance, as shown on the right, with the red lines being the sampled frames. This helps the neural network learn to generalize and not recognize the data. Another data augmentation technique that we use that is very common in image and video-based models is image changes, such as flipping the image, as shown in this repeating video, zooming, where we change the size of the image, rotation, where we rotate about the image center, translation, where we offset horizontally and vertically, and finally brightness, where we change the image intensity. Here all the changes are shown for a single image, but of course in our system it's applied to all the images in the sequence. It might seem obvious to a human that these are all images of the exact same embryo, but for a computer even slight variation can change its perception. And that's why it's so important to do these augmentations. We are extremely proud of the great amount of diverse data that we have used to train iDAScore. But why is data diversity so important? Because AI learns all properties present in your data, want it or not. And it obviously cannot learn what is not there. Therefore, a lack of diversity may lead to poor AI performance for specific subgroups, leading to unwanted bias in your predictions. We currently have a dataset containing many different clinical practices, with embryos going through frozen and fresh transfers, being PGT analyzed, inseminated using ESHRE and IVF, donor oocytes, many different types of media makers and media changes, ages ranging from 18 to 52 years, and data from 3 continents, and probably a lot of other variation that we are not even aware of. Data diversity is a task we will continue to improve upon, even though we believe we have already come far. Today, I would like to share the performance of some of the subsets that we can make on this huge data set. First off, let's look at the individual clinic performance computed on all our data. To evaluate models' ability to generalize to new and unseen clinics, we have performed what's called a holdout test on the 12 clinics that have contributed with the most data. Each clinic was evaluated on a unique model that was trained on the remaining clinics' data, so that no data from the clinic being evaluated was shown during training. Here you can see that all the models resulted in an AUC above 0.9, which indicates a great generalization across clinics. Now let's take a look at the performance by patient age on our holdout test dataset. To make it clear, we did not include age as a parameter to the AI. We just evaluated here. We have divided age up in 4 groups with several thousand embryos and hundreds of positive fetal heartbeat in each, making it possible to compute statistics. The confidence interval for each group is shown as a range on top of each bar. All AUCs for these groups are above an impressive 0.93, showing great performance regardless of age. We do notice a slight trend of decreasing AUC with age though, which can probably be explained by maternal factors playing a more pronounced role with age, whereas iDAScore only accounts for embryo factors. And again, age is not part of the input to iDAScore. Another split we can make on our test data is by insemination method. Again, we see great numbers with more than 5,000 embryos, and though there is a small missing part of the data set, like 45%, that was either not labeled with insemination method or was labeled with both, ESHRE and IVF. Again, we see an impressive AUC of more than 0.95, and the difference between the two is probably due to the difference in clinics performing the different operations. Another interesting split we can make in our holdout test set is by incubation time. We have not just split the data by day of transfer, but subdivided day 5 embryos into 4 subgroups. Earlier than 115 hours, 115 to 117 hours, 117 to 119 hours, and 119 to 130 hours. And then there's, of course, day 6. We see great performance for all these groups, with AUCs being above 0.91, but there is a small decrease on the early and late day 5 transfers. This is most likely because certain clinics contribute more to some groups than others, and that the performance on the different clinics differs slightly. Okay, and finally, let's take a look at the performance of 2 single-step media types used at a single clinic during an overlapping period of time. We see for each single-step media type a very similar performance to the overall clinic AUC, which is 0.92, and that indicates a really good and robust evaluation regardless of media. And again, having an AUC above 0.9 is really, really great. Although all these evaluations on subsets of retrospective data tell us a lot of valuable information about iDAScore, we want to validate safety, performance, and consistency prospectively through a randomized controlled trial. And that is why iDAScore is currently being tested in an international multi-center RCT together with Vertis Health. We look very much forward to sharing the results of the world's largest prospective randomized control to evaluate an AI performing embryo evaluation. So how do iDAScore actually integrate with our system? As always, our incubators send time-lapse information to the ESHRE system in the middle here that stores and processes the information locally on the system. iDAScore runs alongside with the server on the same hardware and thus require no additional costly hardware or any communication with the service in the cloud. To inspect and evaluate the scores from iDAScore, we introduce the new Vitrolife Technology Hub platform. So let's take a look at that. iDAScore is an optional feature of our new Vitrolife Technology Hub platform. Selecting the iDAScore module, you can inspect and evaluate all embryos from any treatment. Simply find the patient treatment and select to initiate iDAScore evaluation. As you see, iDAScore is instantly available for all active day 5 treatments. The AI also automatically detects the number of pronuclei, which is highlighted for all abnormal embryos for easy overview. Individual embryos can be further inspected to check all focal planes and the entire embryo sequence. After manual inspection, the appropriate embryos can be selected for either discard, in the case of the 3PN here, or for transfer and freeze, using the icons above. Because the analysis is fully automatic, it's not affected by embryologist experience level or time available during periods of high workload. And finally, when all embryos have been selected or deselected, the treatment can be finalized and an embryo decision report can be generated for later clinical use. Let's take a look at a few iDAScore embryos after 5 days of incubation alongside with their time-lapse videos. The left one never actually reaches the molar stage, and you can see here how iDAScore also gives it a low viability score of 2.0 from a range of 1 to 10. The middle one reaches the blastocyst stage, but ends up at what we would probably call a poor quality blastocyst, getting a medium score of 6.3. And then finally, the right one develops into a top quality blastocyst and is also given a high score of 9.5. Again, iDAScore's strength is to make robust evaluations of all embryos on all levels. So to sum up, iDAScore provides an instant evaluation with consistent predictions that we have shown are robust across several subpopulations. The algorithm was developed using more than 115,000 embryos, all using full time-lapse sequences, because we know that such sequences contain more information than single snapshot images does. iDAScore will be an integrated part of new Vitrolife time-lapse systems and thus provide a new fully automatic tool for embryo selection that requires no manual annotations and no extra workflow. As a final validation of iDAScore, a randomized controlled trial has started together with Virtus Health, and we look forward to sharing the results in the future. With that, I would like to thank you very much for watching this presentation. And if you have any questions, please feel free to reach out. Thank you.
Thank you, Jens. In closing the session, I would like to thank all 3 presenters, David, Aengus, and Jens. Of course, thank you to the audience for attending. And I'd like to direct you to our website for further information. Also, if you have time, please visit our virtual exhibition booth. So thank you again, and please enjoy the rest of ESHRE.